Please let me know when you want me to start. You want to wait a few more minutes? It's up to you.
Let's start with this first one. Yes, it's started. Thanks. Floor is yours.
Okay, I'm working on two different monitors at the moment. I'm presenting on one and I'm talking on the other. So before I start, please feel free to interrupt me at any given time. But because I'm using two different machines, it might be difficult for me to figure out if anyone is talking to me. So either feel free to leave a message on the chat or just unmute yourself and ask a question at any given point. Every once in a while, I will try to stop and ask you some questions just to get some checkpoints, just to see where progress, to check out we're all on the same page. I apologize from the beginning. The presentation might seem a little bit introductory, but I'm working on the assumption that some of this material, if not all, might be new to some people. So I thank you for your patience for the next couple of hours. At the beginning of the presentation, we're just going to be talking a little bit about the resources that we have available on BIL. Then we're going to talk about some of the software that we use on our hardware, like the scheduler and how we use software on BIL. Very simple introduction just to give you an idea. These are standard tools used in HPC clusters all across the United States. So some of you might be familiar with these if you have worked with other XSEED projects in the past, like Bridges True. This is very standard. And then we're going to be talking a little bit about Singularity. I'm going to do a hands-on exercise if you want to follow me as I present a very simple container. You're more than welcome to do the exercise with me. Like this presentation will be recorded. So if at any given point, you feel lost, you can always go back and try to redo it yourself. The point of this presentation is not trying to focus on the science that you can on the technology. So you're going to see that some of the tools that we're going to put in a container are kind of trivial, because what I want to highlight is the fact that you can put applications in containers. And when we get to the workflows with CWL, you're going to see the same. You're going to see the same scenario where, like, the tool that I'm trying to create a workflow on, it's going to be a very simple application. Then at 3 p.m., there's going to be another presentation where they're going to talk to you, Jeff and Min. They're going to be talking about a more appropriate scientific application using containers and CWL. So that presentation will probably have a little bit more impact, but it works on the assumption that you understood the process that is happening during this presentation. So with that, let me start. I forget that I'm on a different machine. So before we start, I just want to point out something that Alex said this morning. At any given point, you have troubles accessing some of the resources on BIL with your account, accessing software, any kind of questions that you have regarding BIL, please send an email to support, and either me, Luke, Mariah, or someone else in the team will try to answer as soon as possible. And then some very important things when you're using our resources. In this slide, you can see the location of the data where Lydia put the images that you're going to be using for the hackathon. The images are also available over HTTPS. If you want to download them, that's absolutely fine. Then the other question is, where do I put my output? There is a general location that we have created on BIL where you can save your output. This is a shared resource. So the idea is that if you want to share your output within some other members participating in the hackathon, you can put it there. This folder is also available over HTTPS. So if you put a file there, it's going to be available to the public. So keep that in mind as well. Then there is no quota on your home directory. Okay, so you can use as much space as you want, copy images, etc. Just be mindful that this is a shared resource. So, do whatever you need to do, but, keep in mind that it's a shared resource at the end of the day. The same applies with the share space in the hackathon folder. There is no quota at the moment. And then the home directories and data folders. Oh, seems like I didn't finish that sentence. They're consistent all throughout the hardware, meaning that whether you're sitting in the virtual machines or you're sitting in one of the large memory nodes, the location of your data, your code, etc., will remain consistent. So you don't have to worry about moving files or copying files to different locations as you change the resources that you're using. And then last, you can find the BIL Hackathon documentation. At that link, if you click it, I share the presentation link over Slack. Over Zoom, and I also share it over Sulip. And if you click that link, it will take you to sort of like very complete documentation of what you can use and kind of use. It's definitely more complete than the presentation today. Now, what hardware do we have available? So we have two virtual machines. One is called Workshop. The other one is called Workshop 2. The main difference is that Workshop 2 has two NVIDIA V100 GPUs that could be used for GPU computing. You can access either Workshop or Workshop 2. That's absolutely fine. Those two resources are available. The difference is that the GPUs on Workshop 2 are not managed by the scheduler. So the way you can access them, it's a little bit different. If you want to use these resources, just let us know and we'll give you instructions on how to access them. I'm not going to cover them during the tutorial today, but know that you have these two VMs that are pretty large that you can access at any given point. And then we have 8 large memory compute nodes that are managed using a scheduler, using Slurm. And then you can slice them and partition them as needed, depending on the kind of computation you want to do. You can connect to Workshop. Yeah. Sorry, I thought someone said something. Did someone say something? No? Okay. And then you can connect to Workshop or Workshop 2 over SSH, or you can use X2Go, which is a client that, it's like a remote desktop connection, a client. And like I said, the instructions, I'm not going to over the instructions on how to install X2Go. They're pretty straightforward. However, at the bottom of that slide, if you click it, it will take you to the complete hackathon documentation. And there you can find detailed information on how to set up X2Go so that you can use basically a remote desktop connection. And if there's an application that requires you to visualize your images or check the output, etc., this is a good alternative for you to visually explore your data, or if you want to explore your data, even the raw data that's available for the hackathon. There are some common tools available like Fiji that you can use. There's ITK. There are some ITK tools also that you can use to visualize the images. So that's a good tool to use. And then of course you can use Terminal. You can SSH in either of the two Workshop VMs, and from there you can access the large memory nodes. Again, the detailed instructions on how to connect, you can find them in the documentation. You'll notice that during this presentation, I'll put references to that larger documentation because it provides more detail. And for those of you who have used SSH before, then you do everything over Terminal. And then in terms of that, well, every major OS either has a Terminal client or you have the possibility to download one. PuTTY seems to be the preferred one for Windows users, at least in our experience, but you can use whatever you want to connect to our resources. That being said, you can also use X2Go to visually connect to the Workshop VM, and then you can open a terminal within X2Go and use the resource from within X2Go itself. So you have multiple ways to connect to it. You cannot access the large memory nodes directly publicly. So in order to use those large memory nodes, you will need to connect to the Workshop VM or Workshop 2 VM first. Those are publicly available. They have public facing IPs. Okay, so far I'm assuming that that was a very gentle, very generic introduction to how to connect to our resources. I'm assuming that most people has experience using SSH or using Terminal to connect to resources like this. This is a very standard practice. So the next tool that I want to talk about, and I don't want to spend too much time, is LMOD. So LMOD is a module application that we can use to load tools into Workspace. Okay, LMOD can be really complicated, but the only 3 things that I want you to know about LMOD is how to list the software that we have available on BIL, and then how to load a specific module. Okay, the idea to put things, we have modules, is that at different times we may have different versions of the same software that might conflict with each other. The versions might conflict. So using LMOD allows us to have like different versions of the same software. The example for us is bioformats. We have like 5 or 6 different versions of bioformats for different reasons. The second one is Anaconda. You might have an outdated version of Anaconda that it's being used by a researcher or a scientist for specific reasons, but we want to upgrade and have a new version available for other users. So the first command is module avail, and that simply lists all the software that we have available for you. This is a short list of some of the software that we have available. So all it gives you is the name and the version of the software that is there. For example, ITK, it's installed. There's some other like different versions of Java, ITK Snap, which I believe ITK Snap, it's a GUI-based tool for exploring nifty images. So there are different kinds of tools that we prepared and package and deploy for you. If at a given point there's a tool that you need access to and it's not available here on this list when you run module avail, just send an email to BIL support, and we will try to figure it out if we can deploy the software within the time frame of the hackathon, or we will let you know if that will not be possible, but just keep that in mind. The second command is module load, and this is very straightforward. Once you list the software that we have installed for you and it's available on the system, then you just load it into your workspace in your current session, and then becomes available to you. In this example, I'm using MATLAB. I know for this hackathon, we're trying to keep it open source, and I guess MATLAB is not open source at all. But the main reason for me to mention this is that if at any given point you do need to use MATLAB, you do have to request access to the software. So at the bottom of this slide, you'll see a link that it's also available in the full documentation. You have to go to our website at psc.edu, and then you need to fill out a form before we can give you access to MATLAB. So keep that in mind. That might be a nuisance. And then Anaconda, I mean, maybe I'm biased, but I think a lot of people are going to be using Python for this. But that's my own personal bias. You can do module load Anaconda 3 and it will load. I think it's version 4.11, the one that we have deployed, the latest one. We do have some older versions, but they're currently not maintained, and they're there in the system for mostly historical reasons. And like I said, LMOD is very complicated, but these are the 3 basic commands that I want you to know: how to load, how to unload, and how to list. And when you write your scripts and you need to use more than one module, you simply list all the modules that you want to load. If there's going to be a conflict between them, the system will let you know that they cannot work in the same session at the same time. But most of the software that we have installed will not have any issues like this. So for example, in this particular case, Glencoe Software, the developers of bioformats, we have 3 different tools. So we load 3 different modules at the top of our script. That's absolutely fine. Keep in mind that if you're submitting jobs to the scheduler, you might need to add all of these module loads to the top of your script, especially if you're trying to do something with Python. You might need to run module load Anaconda at the top of every script. Okay, so that puts a stop at LMOD, right? Like LMOD, we just use it to load software that we can use in the scripts that we use either on the workshop VMs or in the L nodes. Okay, so any questions so far? I don't see any hands up. Okay, good. Wait, I don't see it. Let me. Sorry, it's just that it's difficult to use 2 different screens. Okay, perfect. Okay, so no questions. So I'm gonna go on. So the next thing that I wanted to talk about is Slurm. So Slurm is our workload manager or scheduler, and we use Slurm so that we can submit jobs that can be scheduled and run in the large memory nodes. Like I said, we have 8 large memory nodes. The benefit of using Slurm, with just being a scheduler that determines what goes next, is the fact that it allows us to slice the large memory node into pieces that we can efficiently use, and more than one person can be using the same resource at the same time. It's pretty standard software. Again, Slurm, just like LMOD, it's kind of complicated and convoluted at times, but they're just 4 commands that I want you to think about while working in the hackathon, if you have no experience with Slurm. A lot of traditional or more stable HPC clusters tend to use PBS. So if you use PBS before as your scheduler, Slurm is pretty similar. And so the first command that I want you to think about is sinfo, and it just simply lists the resources that you have available. If you're part of this hackathon, then running sinfo should list something like this. It's just listing the nodes that make up the compute partition. And the compute partition is the partition that you have access to as a member of this hackathon. If you run sinfo and this list comes empty, then there's certainly something wrong, and then you should send an email to BIL support and we can take a look. But everyone should be able to run this and see it. So for example, if I go to mine and I run sinfo, I see a little bit more than other people just because I have access to an additional partition. But sinfo should print something like that, okay? The next command that I want you to take in consideration, SQ. And SQ, all it does is just that prints the job sitting in the queue. And it will give you an idea of the status of your current jobs, but it will also list every single job that it's sitting in the queue, including all your collaborators. So it can sort of give you an idea if you're going next, when you're going next, if you have to wait, how many people are running jobs at the current time. Let me see. If I run this, I should see nothing, I guess. Oh, well, someone is doing an interactive session. So there you go. So that's it. So there's only one person. It doesn't seem like they're using all of the resources. So some of you might request more. Again, sinfo and SQ. The next one is sbatch, and sbatch is the most widely used, probably what you're going to be used the most, and it's the command that you use to submit your script to the scheduler. And if you look at this simple script that I have on screen, it's very dumb. It's very straightforward. It just loads Anaconda and then installs cowsay, which is a dummy application that pretty prints a cow saying a word. But technically speaking, this should work on BIL. And then when you create this script, you can submit it to the scheduler using a command like this, which is nothing but your script that has your commands. Now, for this hackathon, it's very important that you keep in mind of these 2 things that I highlighted, okay? First is the reservation, because half of the compute nodes that we have available on BIL have been put in a reservation just for us. So for the next 3 days, only members of this hackathon should be able to access these nodes. And then the account. The account tells us where to charge the allocation. So it's important that when you use sbatch to submit your job to the queue, that you use these 2 parameters so that we know that you're a member of this hackathon. And you should also be able to put the partition or the queue, which in this case is compute. So this command should be consistent with everyone who's working in the hackathon for the next 3 days, except maybe the name of your script could be something different, okay? And then if this works correctly, you should see a message like this one, that it gives you the number of the ID of the job that went into the scheduler. If you do that, and if your job is long enough, running SQ should put your job, should show your job in the queue. And the thing about sbatch, when you submit it to the scheduler, if there's any standard out print by your job, then you're going to find that it creates a file called slurm, the job ID.out. In this case, like I said before, cowsay, it's a very dumb tool that just prints a cow saying a message. So in this case, it's the output of me submitting the script that I showed 2 slides before. I created my simple script, I submitted to the scheduler, it ran pretty quickly, it printed out to screen, and then it put the output in an output file. If your job is saving files to disk, then you should find those files to disk, on disk, assuming that your job ran properly. The maximum wall time for jobs in the scheduler is 72 hours. So it's very common practice for people submitting jobs to SBatch to put some checkpoints so you can resume your job in case your job fails or in case you run out of time. So keep in mind, putting checkpoints in your code is, I would argue, it's a sort of standard practice for many people, especially when when you have a limited wall time. And there's some other options that you can use on SBatch. The most important ones is the last one. So you can aggregate them all and you can specify the number of cores that you want, assuming that your tool can exploit hyperthreading, or can use more multi-core, or you can use more memory than needed, or you can scale properly. Then you can use SBatch to slice more resources from one of the compute nodes. Keep in mind that allocating more than 1 or 2 cores for a particular job, but your tool or your code is not able to use more than 1 core, will only waste resources, right? Like Slurm is not intelligent in the sense that it will get the resources you requested, but just because you got those resources does not mean that it automatically knows how to use those resources if your code doesn't know how to do it. Okay, and again, like we said before, the amount of RAM and the number of cores is different between the Workshop VM, Workshop 2, and the DL node. So you can sort of navigate and figure it out how much memory do you need. Also, the one other thing that I want to point out is that Slurm is not flexible once it allocates the resources. So if you consider the example on screen, I allocated 128 gigs of memory. If at any given point my script tries to allocate more than that, the job will fail. It's not flexible, it will not scale up. So keep that in mind. Sometimes you might see some error in the output file in terms of memory. It might be that your code is trying to use more memory that you allocated on your Slurm job. So increasing it a little bit or increasing or scaling it tends to be a common solution at times if you don't want to optimize your code. And that's it. And the last command, it says cancel. If you want to cancel your jobs, there's ways of canceling every single job that you have on the queue, or you can cancel a single job. And that's pretty straightforward. So now we know we have LMOD to load the software in your current workspace, your current session, and then we use Slurm as a scheduler to manage jobs that we submit to large memory nodes. Keep in mind that the Workshop and the Workshop VM do have a lot of resources, but those are not being managed, excuse me, those are not being managed by Slurm, meaning that, if the 33 of us or 60, I don't know how many people are here now, connect to the Workshop VM, we're all competing for the same resources at the same time, and it's not getting partitioned or sliced like the scheduler does with the large memory nodes. Okay, so any questions so far? This is sort of an intro. I guess no questions, that's good. Okay, so the next thing is, I mentioned before that Slurm is kind of like a complicated tool, and it does have 2 tools within Slurm that you can use to start interactive sessions. So not everything needs to be submitted to the scheduler. However, at PSC, we develop our own in-house script to start interactive sessions, and that is called Interact. And Interact is pretty straightforward. It works very similar to SBatch. You just, you tell it the reservation, the partition, the account number, the number of cores, the amount of memory, and it just starts a bash shell in session. So for example, if I am here and I want to say, well, I want to do 10 cores, 16 gigs, and do Interact, it will eventually put me, now I'm queued, but it will slice those resources of a compute node. And now you'll notice that I'm sitting in a compute node. That's why it says L001. And this session that I'm sitting on right now has 10 cores and 16 gigs of memory. And you can use this for debugging, for editing, for exploration in general before you submit your jobs to the actual scheduler. It's very good for exploration. Just keep in mind one thing about Interact, it keeps track of your session, in the sense that if I don't use it for, I think it's 5 or 6 minutes, it will kick you out. So keep that in mind. You might need to then request the allocation again, so that you can get the same resource. And that's just to be fair with the other people who might be accessing the shared resources. And again, what I said before, plus now we use Interact to start interactive sessions on the large memory nodes for debugging, exploration, whatever you need. So far, any questions?
I have a question for you, Ivan.
Yeah.
Has anybody used Dask on top of Slurm?
You can use, you mean, yes, I think I have tested Dask, and I think Alan has used Dask before. We have both sort of explored, but just to figure out how to make it work, I have not done any real, real life applications on using it, but it should work.
Great.
It should work. If you allocate the resources properly, it should work. I don't know if Alan, you have anything to say about this? I guess not. Okay. And if you want to try, you can try it. But we can talk offline and try to figure out if there's an issue, we can make it work.
Sounds good. Thank you.
Okay, so that was the part of the presentation that was just like very basic. This is how we do things at BIL, right? Like this is what you have available. Like I said before, these are very standard packages in HPC clusters used all over the world. If you use Exit resources, these are very straightforward. What might change in relation to other large computing resources is the amount of compute nodes, or the amount of software it's installed, but it's the same idea. So the next thing that I want to talk about are containers. So who has experience using Docker? Can you raise your hand using the little raise hand? Who has experience with Docker? I don't see any raised hands. Nobody has used Docker before or heard of Docker before. The silence. Oh, I see a couple. Okay, good. So you have used Docker before. So Docker it's widely used, of course. In the last few years, sort of exploded. It's pretty flexible. It's widely used in science, but it does have some limitation in terms of HPC clusters, in the sense that there's certain level of permissions when you give access to a person using Docker, especially when building containers, that we tend to frown upon for different reasons. So that's why a lot of HPC clusters do not support Docker, though there's some alternatives here and there. So Singularity doesn't start out of a solution for HPC, but it sort of does. So Singularity, now known as Aptainer, which is the open source version of what used to be Singularity, is mostly used to deploy software. Now, if you talk with a lot of people that use Docker, they really love Docker to deploy microservices, which in general we don't do as much in science for this kind of applications that we're talking about today. So what people like to use Singularity for is just to create containers for their applications, Python scripts and Perl scripts, or outdated software that has not been updated in 5 years, and it's using an older version of maybe Python 2, or an older version of Perl, Fortran. Singularity comes to the rescue and makes it so easy to create a container that works out of the box, that works with legacy software. So that's the first thing. So now just like Docker, for people who used Docker before, we do have a definition file, and the definition file is nothing but the set of instructions that builds your container. It's just a regular text script, a test file, sorry, that that has instructions on how to install software. And then you have the Singularity image file, which is an actual file that lives on disk, and that is the container. That is one of the main differences between Docker and Singularity. In Docker, with Docker, your images sort of exist as a binary blob, most of the times in a shared space between multiple users and on the same machine. And so with this, with Singularity, each of us could have our own copy of the container, or we could share the same container file if needed. But at the end of the day, it's sort of pretty flexible. So let's start talking about the definition file first, because I think that will make it more clear. So if you look at this, what you see on screen, this is a definition file for a container that is running bioformats to raw. Bioformats to raw is a tool developed by Glencoe Software that takes an image file supported by bioformats and converts it to SAR. It explodes in a million small files that makes up the SAR file. But you can also compute image pyramids on that image. So it's a widely used tool. So in order to build a container from this, all I needed to do, and this is going to be the case, especially if you're going to using tools developed by somebody else, I just went and looked for the documentation from Glencoe, and they provide me with the instructions that I needed to run on my machine to install bioformats to raw, and then I tweaked those instructions to work within a container. So a lot of times when we build a container, we start with the minimal container that we can get. In this case, I use a Debian distribution, and then I just installed the 3 or 4 dependencies. I installed Java needed by I installed OpenJDK and wget on zip, all of the things that I needed to download the package from the web, just unzip it, putting it in another location, and that's it. That's all the container is. Okay. Now the first part is the section where we define what is the minimal entity that we start from. I started from a Debian distribution, but in reality I could have started from an Ubuntu one. It doesn't make any sense. It doesn't make any difference. Sorry. The Ubuntu distribution might be a little bit more bloated, might be a little bit larger. At the end of the day, it's a matter of preference, to be honest. If you have experience working with one over the other and that's the one that you prefer, that's absolutely fine. A lot of people working with containers try to avoid bloating the container, making it larger. They just like small, flexible, and useful containers. But at this point, I don't think that's the purpose of this hackathon. It's just to containerize applications that work. You can spend some time making them more optimal or minimizing the space, but it's not a big deal. And the second part is the part where you define all the environment variables needed for your container to work. In this case, because it's a Java application, I needed to define the location of Java within the container, and that's all I did. So that every time that I call my container, it knows that it needs to export this variable in order to work properly. Very straightforward. And then the post section is where I just provide with the instructions on how to install the software. And in this case, like I said, I use aptitude to install the dependencies that I knew from the documentation provided by Glencoe. And then all I did is use wget to download the software from GitHub. I put it in the right folder, I unzipped it, and I made a soft link, that's it. And it's done. And then I do an aptitude clean sort of to, make the image a little bit smaller. It doesn't make that much of a difference. And then the last one is what we call the run script. If you're familiar with Docker, this is similar to the entry point, meaning that when you call the container, sometimes you define an entry point, which is the default script or binary or application that gets run that lives within the container. So with Singularity, you can do the same. So because I have a single container that has one tool, which is bioformats to raw, I just said, well, if you try to run the script, the entry point should always be that binary. I don't care about anything else that lives in the container. And that's basically it. So let's do something. Let's try to do this example together, okay? So let's take a couple of minutes. Everyone try to log into the workshop VM. By the way, is the font too small at the moment, or is it large enough?
I think it's fine.
Okay. Like I said before, every single example that I'm discussing today, it's available on a repository, so you should be able to recreate everything. So everyone, please try to log in and raise your hand on Zoom whenever you're ready and you're logged in into the system. I'll give you a couple of minutes to do this, and then we can start. We can go on. Okay, so let's start. Before we start with this example, let's do one more thing, okay? So one thing that it's mentioned in the documentation, I didn't mention in the presentation, is the fact that when we build Singularity containers, we create that zip file, okay, which represents our container. Unfortunately, due to limitations on your accounts, you're not allowed to build your containers on BIL. But what you can do is use a remote builder. What the remote builder does is that it sends your definition file to Scilabs, which is the company in charge of Singularity. It builds the container in the cloud, and then it downloads the container back into BIL. And we can do that pretty simply on BIL. However, the first thing we need to do is to generate a token on the Scilabs website. So let me show you. So everyone, please go to scilabs.io. Open a browser and just go to scilabs.io. It should take you to a page that looks like this. And then just click on Cloud Login. And you're gonna click on Sign In here at the top. In my case, it's signed in already because it knows who I am. But the first time you clicked, it will ask you whether you want to sign in with your GitHub account, with your Gmail account, with Bitbucket, GitLab. I forget, there's like 5 options. Choose whatever option it's good for you. It doesn't really matter. And I'll give you a minute to sort of do this. Okay, so assuming that everyone was able to log in properly into Scilabs, when you click your username at the top right, you're gonna see that it asks you about the access tokens. So just click that and it will take you to a page that looks like this. I already have a token, but I'm gonna revoke it. And once you're here, just create a label, whatever you want to call it, and then click on Create New API Access Token. And it will create one for you.
Ivan, how did you get to that page again?
So when you went to, were you able to log in?
Yes.
Okay, so your username should be at the top right.
Yep.
Click on that and you're gonna see access tokens.
Okay,
see
I
it?
got it. Yep, thank you.
Okay. So then you need to give it an alias or a label. And it will look something like this, what you see on screen once you create a new API. And then you can just click on copy to clipboard and it will copy it into clipboard. And then I'm gonna go back to my connection on the workshop VM on my terminal. And I'm gonna type Singularity remote login. And then I'm gonna click enter. And it's gonna ask me, well, in my case, it's gonna ask me to replace my old token. I'm gonna say yes. But if this is your first time, it's just gonna ask you what is the token. And then I'm gonna right click and paste it. I'm gonna click enter. And that's it, I'm ready to roll. So again, you created your new token on the Scilabs page. And then I copied it to clipboard. Then I went back to my terminal and I typed Singularity remote login. And then I follow the instruction and paste it on terminal. And if it worked properly, it should say something like access token verified. Are we all on the same page? Thumbs up if you are. Thumbs up. So let's give it a minute. BIL worked for me. Very good. Good for me. Okay, perfect. Okay. So the main difference now, I'm going to go back to the presentation. In my case, I'm just going to go to the desktop, but you can go anywhere in your home directory. It doesn't really matter. And I'm going to run the first command, the git clone command from slide 33, sorry. And that should clone my bioformats repository. And I'm going to CD into the repo. And I see, let me make this a little bit larger. I'm going to CD into my repo. And I see a bunch of files. And there's a folder called 3.00. If I go there, I'm going to see the files that you see on screen, right? So the Singularity file is the same definition file that I showed you before, right? The main difference is that I have a label section, and the label section is how you can say in a key value map of things. And all of our images created at PSC have this sort of header, so we know who created them and that we created them basically, but you don't have to do that part. And like I told you before, we started with the Vian image and then we followed the instructions. We created the variable, we created the entry point, and we follow the instructions on how to. Now, if you look at all of my—
So, Ivan, can I interrupt you for a minute? So I must have missed a step here when you got this Singularity bioformats to raw. Did you copy something from somewhere?
Yeah, I cloned it.
That's what I'm missing. Okay.
So if you go to slide 33 in the presentation, that's where the command to clone is.
Does that GitHub have some sort of access
No,
login?
no, it doesn't.
Oh, it doesn't
You-
work for me, but that's okay. If it
You might
works for
need to
others-
set up. You might need to set up your SSH key so that you can clone over SSH. You know what? Let's do something then. if people are gonna have that problem. So if you, let's see, it's called build data hackathon. Okay, there we go. So if you go to this folder, I'm gonna copy the command. I copied over, so all of you should be able to do copy. Okay, for your benefit, Lydia, I put, let me see, where's the chat? Chat. Okay, I'm gonna put the command on the Zoom chat. If you run that command, it will copy over that folder that I cloned. Or you can run, or you can run the command that Yana just copied. That's a good thing. That's a good. I'll make a note of that. Okay, so now we're all in this bioformats to raw folder, and there's a folder called 300. And then when I go inside it, you're gonna see there's a singularity, definition file, and this has all the instructions to build the container. Now, if we go back to the presentation, you'll see that there's this command at the bottom. It's the singularity command, but because we're using the flag remote, it will send our recipe to Scilabs. It will build on the cloud, and then it will download the file. And the image that we're gonna get from Scilabs is gonna be called bioformats to raw.cif. So I'm just gonna copy this command in slide 33. And I'm gonna go back to my terminal. And this assumes that I'm in the same folder as where the singularity files lives. And crossing fingers, you should see something like this, where it's verifying your token, and you see some good messages. All of this is happening on the cloud, and you're getting the output on your screen, but nothing is happening locally. It does take a little while to build everything on Scilabs and to get it back, so let's just wait. Now, I will say something though. The only limitation of the remote builder is that you cannot copy local files into your container. So just like with Docker, you can copy local files in the image itself. But if you're doing a remote build, you cannot do it this way. So what I had a conversation, I think, with Jeff about this before. And what you could do is that you could put your images, or you could put your source code or whatever it is that you want to copy in your container in the build data hackathon folder, which is available over HTTPS, and then have a wget or a curl command within your container to pull those images from our build resources, and that should work. So if you take a look at the singularity definition file for what we're building right now, you'll notice that I use wget just to download a file. So you could do potentially the same thing. Okay, so it took a couple of minutes to build. And now we're downloading. So now we have to wait. It does take a little bit to build. Any questions so far? Does anybody have questions while this is happening? No questions? Okay. Okay, it's done. So now I can see that in my home directory, I have a file called bioformats to raw that it's about 400 megabytes, give or take. And that is my containerized application. Could we make this into a smaller image with a smaller footprint? Maybe, I don't know, but this should do for now. This works. So let's go back to the presentation. Again, this is the kind of output that you are going to see if it runs properly. It takes a while to download. Now I see that I have the ZIF file in the directory where I built it. That is my container. And by the way, if you build, you could potentially build your container locally in your laptop if you're running Linux or your desktop, and then you can SCP or rsync the file into BIL and it will work. Okay, so you could potentially build a local image and then just copy it over. So how do we know that this works? Well, we know that the application that we exposed was bioformats to raw. So let's see if we can make it work. So the way they use Singularity is that you say, well, I want to execute something that lives in that container. And the something that I want to execute is bioformats to raw. But right now, I'm mostly interested in printing help. However, you might need to create some bind points. So I'm going to make sure that whenever I do this, we're mounting BIL. So whenever you're running something in our hardware, you will more than likely need to include this Singularity/BIL. Okay. So hopefully I'm going to get the help output. There you go. Okay. Right, so did not work. So bioformats to raw complained that I didn't give it any input. You're gonna see it at the top. And then it decided to print all the help. So that worked. Right, so I was able to run the application with the container. For most, so this is where you learn the little tricks. I don't think any of you are gonna be doing Java, but setting the Java home, it tends to be the biggest pain of building Singularity containers that use Java. Setting the proper variables, the Java options, and the Java home, and using the proper version of Java is the biggest pain of building containers with Java. Okay, so this seemed to work, but beyond printing the help, we want to do something useful. So what is it that we can do? Well, we got it to print the help and it works. But then there's the other question is like, but you know, like if Glencoe is using a lot of effort into building these containers, why I'm going to build a container myself? And that's true. Most of the times you're going to be working with collaborators, with other labs, with other institutions that they build and support their own containers. So you really don't need to build them every single time. Okay, if that is the case, Singularity will allow you to pull the container and build it from an existing container in Docker Hub. So I'm just going to copy this command. And by the way, I pointed out here as an example, the only reason why I'm doing this with Glencoe is because I know them and I trust them. Please don't randomly pull containers from the web just because you found them in Docker Hub. Unfortunately, there have been some cases where people inserted malicious software in containers, sometimes for mining, for crypto mining, So just be aware that you either trust the person or the group that built the container, or that you have the Docker file available so you can see what's really installed in the container itself. So in this case, I can run the command singularity pulled from Docker. And if I run this, it will, well, in my case, I already did this, so it's using a cache image. But if you run this now, you're gonna notice that it's gonna start converting that Docker image into a singularity file. And now you're gonna see that I have a zip file here, that's the zip file converted from the singularity image. Now, if I do singularity shell bioformats, I can shell into the container. And I can see that bioformats to raw, well, here you go. It's available on OPT bioformats, right? So that's a little bit like this. I wanted to point it out. I said it in the next slide. I downloaded. The main difference between the image that I built myself and the one provided by Glencoe is that I provided an entry point so that I always know that bioformats to raw is available. But in the one provided by Glencoe, it is not. So I need to know the full path to the binary in order to call it. It's not a big deal, but it might require a little bit more exploration if you did not build the container yourself. And if you notice this singularity call where I'm using the one that I download from Glencoe, instead of calling directly bioformats to raw, I had to put the full path to the binary inside the container in order to call it properly. It's a small detail, but sometimes, it is what it is. So any questions so far? So now that we talk about, yeah. I thought someone was talking. No? Okay. So we can use Singularity to build containers that can be run on HPC clusters. They're widely supported, they're widely available. If you find an image on Docker Hub that has an application that you trust, from a developer that you trust, you can simply pull from Docker Hub and convert it into Singularity. You need to know what binaries are in the container or the location to the binary if it's not on path. That might require a little bit of exploration, but it's not that difficult. Or you can build your own container. It's literally up to you. But bottom line is you cannot build containers on BIL, but you can use the remote builder to build it on Scilabs. It works 99% of the time. The only time that it fails is when you're trying to copy a local file into the container, because all you're really sending to Scilabs is the definition file. You're not sending any additional files. So far, so good? Yes?
Yes.
Okay, so sorry, it's just that I'm like between two machines and I don't know if people are saying yes or I'm missing something. Okay, so now let's try to use the image. Okay, if you go to slide 42, sorry, if you go to slide 42, just copy this script and create a file called example.sh and copy the contents of the script found on that slide. I don't know why I did this, but okay. So again, on slide 42, you're gonna see example.sh, just copy those contents onto terminal, create a file called example.sh and just save the contents of the file. And in this case, we're gonna use bioformats to raw to take an existing image in the BIL file system a relatively small image, because we don't want this example to take 5 hours. We're gonna convert it to a SAR file, but we're gonna try to compute image pyramids at 6 levels using a tile width of 128 per 128 pixels. A relatively small task. Okay, so is everyone thumbs up if you already created the file? Thumbs up. Okay, so we're all good. No questions? Okay. So now notice that in the same folder where I have my example.sh file, I also have my bioformats to raw singularity image file, the one that I created in the previous step, not the one that I pulled for Glencoe, but mine. Okay, and then if I look at example.sh, you're gonna notice that I'm creating an alias called bioformats to raw, and that alias is nothing but calling the binary bioformats to raw inside that container that lives in my folder. And I just do that for simplicity, to make it the code easier to read. You don't need to use aliases at all, but this is what makes it more readable for me. And then the input image is a file that exists on BIL, and I wanted to create this SAR folder, which will have the image. So now remember, we're combining LMOD and we're combining Slurm with Singularity. So if I open my example, do I need to load anything? No, because this is not dependent on Anaconda. This is not depending on Java. The Singularity container is self-contained, so I really don't need to load any module. I'm good with this. So now I can submit my script to Slurm, and I'm gonna do sbatch. I'm gonna cheat because I already knew I had this saved. I really don't know how many cores I need for this, but let's just say 4. I don't think bioformats to raw can exploit it, but for the sake of argument, let's say it can. And I don't know, 32 gigs, which I also think it's an overkill. But if I run this command that you see on screen, it should submit that job, knock on wood, and work. Okay, it did submit it. Okay. If you go to my presentation, the command, it should be there. So yes, so if you go to slide 43, you can see the command that you can use to submit this example script. So running that shouldn't give you any issues. If you see an error in a message when running this command, the sbatch command, please let us know as soon as possible, just to figure out if there's something wrong with your account. But everyone should have access to the partition and the reservation and the account.
It didn't like the -r flag.
What, Lydia, what did you say?
It didn't like the -r flag.
What didn't let you do? Sorry, you're cutting. What?
It didn't like the -r flag.
Oh, can you, what did you see?
Wait a second.
What message you got? Oh, because it's not, maybe I wrote it wrong in the present. My bad, you're right. My bad. You're absolutely right, Lydia. That was my fault. I made a mistake, but I can fix it easily. Okay, because it's. Okay, sorry, I gave you the wrong command. Lydia is totally right. So this is the command. If you refresh your browser, you're gonna see the right command.
I don't
So
think there's an equals there.
it worked with me.
Okay.
Where it doesn't work is with interact. Interact and SBatch are different. That's why I made that mistake. See if I remove the equal. Oh, it did work without the equal too. Okay, so you're gonna see that it's running, and now you can see that in my case, now I have a folder. And that folder is called sw17.sar. And now if I compute the total size of that folder, it should be more than a few megabytes because it's that original image plus the image pyramid, or how many levels it could compute. But I asked us to do it at 6 different levels. So were you able to run it, Lydia?
It's there.
Did it accept it? Did it print like submitted?
Yes, it did.
Okay, good, good. And now you wait. It only takes a couple of minutes. This is not a long.
How do you, is there a way for the job to tell you how much resources it has used?
No. Unless you install a tool that can keep track of those resources, Slurm does not know.
Okay, all right.
Can I ask, how do you deal with resource allocation? Like, is there anything preventing you from using like 300 cores?
Well, the fact that we don't have 300 cores will not let you do it. But
Yeah.
so if you request more resources than available, your job will sit there forever, right? Because it doesn't know. It's just waiting for the resource to become available. So keep that in mind. If you request more memory than the node has, then you're going to get an error, which I think, not an error, you're going to get a flag that says waiting for resources or resources not available. But there's nothing preventing you from requesting the maximum of any given compute node. So you could
Gotcha.
potentially request like all nodes. But if you do something like that, we'll probably cancel your job.
Yeah, and I just wanted to
Got it.
mention one thing here too. I mean, in the context of the workshop, we're using BIL resources, which is a cluster that we have dedicated for BIL purposes. All our data is available on our larger HPC system, Bridges 2. So if you have a problem that requires, 100 cores or 500 cores or a lot of memory, that's really the appropriate system to run that type of a job on.
Got it. Cool.
You can contact us and we can help you get started there.
Cool.
What are you doing now, Ivan?
Ivan, I think you're muted.
I was muted, you're right, sorry. I was trying to compute the folder size of the SAR image that we computed in the previous job. That's all I was trying to do. At least to prove that it was not like an empty folder with no content, and clearly it's not it. So I'm going to work on the assumption that our job ran properly. We use bioformats to raw to convert an OME-TIFF into a SAR file. And at the same time, we computed image pyramids at 6 different levels at the most. And then we use a tile size of 128 by 128 pixels. So yeah, so that's a very simple example at which we can take one tool, we can put it in a container, and then we can run the application within the container. Now, keep in mind that when you're working on your scripts, not every single tool has to be inside a container. In this case, it makes sense to do that with bioformats to raw, but you could be working with a Python library that it's working on our version of Anaconda, and then you might have an outdated or a stable legacy code in Fortran that you're putting in a container because it's the only way to make it run properly. So you can mix and match containers because what you're really putting is one application per container. Or, and some people really like to do that, is that they just create a single container that has their whole workflow. You know, they might have like 10 applications installed in a single container, and that it's a preference. Like some people like to do that, and that's absolutely fine. In my case, I prefer one application per container because it makes it more flexible at the time of creating workflows. Okay, good. So we only have about 45 minutes. So let's continue. So we computed, we submitted the job, it went into the queue. Remember, you can always use SQ to determine whether your job is sitting there or not. This was a really fast job, so it only sit in the queue for a couple of minutes, but you know, you can keep track of your jobs. You can take a look at this, at the output file created by your job to figure out at what step of the computation it is. This is really useful if you're running on verbose mode or a debug mode. You can tell what's happening. And then the other question is, can we use more than one container at the same time? And the answer is yes, right? So go to slide 46. And you're gonna see that on the top of the slide, I put a copy command. Just run that copy command on the folder we ran our script. So for simplicity, I created a container with raw to OME-TIFF, which is another tool developed by Glencoe. So bioformats to raw takes a bioformat supported image and converts it to SAR, to raw. And then this other tool takes that raw folder and converts it back into OME-TIFF. So basically what we're going to do is we're going to take that original image, which is a TIFF, we convert it to SAR, and we also computed image pyramids on that image. So we added more to the image rather than just converting it. And now we're going to turn it back into an OME-TIFF. So if you run this command, it will copy, hopefully, a container. And now you're going to see that we have another CIF file. And that CIF file is raw to OME-TIFF. The singularity definition file for this one is also available on GitHub. And it's basically the same thing as bioformats to raw. The only difference is that instead of downloading that binary, I downloaded the other. Could I have put the two binaries into a single container? I could have, but I just created two different containers, one per tool. Like I said, it's a matter of preference. It wouldn't make any difference because both of them have the same version number. So it's absolutely fine. Okay, so now I'm gonna modify my my example script. If you go to slide number 47, you're gonna see that I have a new version of the script. I'm actually gonna copy this, go back to terminal, and I'm gonna call it example2 actually, so I don't have to. And notice that example2 is very similar to the script that we created before. The only difference is that we're creating an alias for raw to OME-TIFF, which is nothing but another singularity command. And it's the basic script from before. It's just that now at the end, we're gonna call raw to OME-TIFF to convert the SAR folder into an OME-TIFF. Now, what I want you to keep in mind, and this will become obvious when we jump into CWL, is that the way that I envision in my scripts is that each of the steps in my script can be a container. So for every single step, I create a different container. Now, this only makes sense if the steps are really different and important. If you're doing something very simple, like, checking inputs or reorganizing data, you might not need to create your own container. But if your steps are significant and you're calling different tools, it might make sense to create different containers for this. So now that I have this, I'm gonna save it. And I'm just gonna call the same. Actually, I'm gonna erase the SW folder. Just because I wanted to start from scratch. I should have not done verbose. I'm just gonna erase this folder. And the main reason for erasing the folder is because I wanted to sit on the queue for a little bit longer for the sake of showing you how it works. Okay, so now I'm gonna run the sbatch command like I did before, but the only difference is that instead of calling example.shell, I'm gonna call the second script, which is the one that I created a second ago. If I click on this, it should assign a number. If I look at SQ, I'm sitting there waiting for my turn. There you go. Lydia, I see that you submitted yours. And now we wait. And it recreated the folder, so it looks like it's at the first step. And that's basically it, right? Like with Singularity, we can create definition files, one definition file per tool. If you so want to, then we can create one container per tool, and then we can mix them together in a single script to create a workflow or a pipeline. This becomes really useful for legacy code, but it is also very useful when thinking about the future. If you build a tool that it's depending on an outdated library from, I don't know, from an older version of CentOS or a version that it's no longer supported or is not supported in the latest distribution, but you really want to upgrade your system, then putting your applications within containers, it's definitely the way to go. Okay, and then we submit it with the same command, and then we wait. And in this case, if it runs, you should see two images that look like this. A single image, sorry. And that's the output of running this script. So let's see what's the status. It's still running in my case. Well, we can let it run. So, yes.
What happens if your code is old and your system is old and you don't really know all the steps to putting your software back together? What do people do? Does copy directories and see which is the minimal spanning set required?
Yes.
Okay.
The answer is yes. The
Okay.
answer is yes. So So I think there are a lot of people who are always, maybe not necessarily in science, but maybe IT managers are mostly interested in minimizing the footprint of the container. But for us, reproducing the results of the tool is definitely more important than whatever space we're losing on disk because of the size of the container. Could we spend a little bit more time trying to make it better? Definitely. But I don't think that's the goal of putting certain things in containers, right? Like some tools, I don't know what comes to mind at the moment, but there are some specific tools that are widely used, say in genomics and proteomics, that have so many dependencies that there's no way that you can reduce the size of the container or depend on other packages, or they build on top of each other. So it is what it is. Like I said, you can build your container locally on your laptop or your desktop, and then you can upload it to your home directory. I do that a lot. I have my own Ubuntu machine that I build a lot of containers here, test them, and then I put them on. By the way, just to keep in mind, if you use, if you have used Bridges before, 90% of the applications deployed by our group, by the Biomed Apps group on Bridges 2, are all deployed in Singularity. So it's transparent to the user. The user doesn't really know that they're using Singularity containers. And that's one of the reasons why we have so much legacy software that can run out of the box on newer OSs. So keep that in mind. Flexibility, it's very important. And then the biggest trick is do not reinvent the wheel. A lot of companies release official images, Ubuntu, Alpine, CentOS. There are official images for Perl, for Node.js. You can find official images for almost every single tool that is widely used in our world. So use those as the base to install your application. Even Anaconda develops their own base images, and Miniconda as well, that you can start from scratch. So keep that in mind. And now I want to present you some examples of Singularity recipes, okay? And I wanted to present to you with this example so you can see the things that you can build. Circos is an application that just makes pretty graphs. I don't know if any of you have used it before. It just makes some very pretty circular graphs. It's widely used. It's Perl. So it can be convoluted at times. So all I did in this particular case is that I just followed the instructions provided by the Circos developers. I started from the official Perl image, and then all I did is install all the libraries that are dependent on Circos, and then I just put it in the right location. That is enough to deploy Circos in a container. And in fact, if you use it on BIL, which is available on BIL, it is running from a container. Then you have other other extreme examples. Alpine is it's a Linux distribution with a really small footprint. I think it's about 5 megabytes for the base image, and it does come with a package manager called APK. And all I did in this particular example, I just say APK install Midnight Commander, which is a file manager, and this created an image that it's about like 7 megabytes or 9 megabytes that is running the tool. This is a dummy example in the sense that maybe it's not needed to create a container from a tool like this, but it shows you how some tools that work out of the box can be deployed very easily in a Singularity container. Then you have something like even CWL tool, which is the tool we're going to talk about next, can be deployed itself in a container, even though it's meant to run containers. And then in this particular case, I start with the Debian distro and then install Python 3. This also works, right? Like I start from a very simple image, I install Python, and then I install all the dependencies that I needed to run that tool within the container. This is a very specific example because the developers of biocontainers, which is a registry just for computational biologists and genomics people, and this is widely used for Galaxy. If any of you have used Galaxy before, Galaxy Server, they deploy a lot of applications in Singularity containers. I found one that works out of the box. So my Singularity definition file is nothing but me taking an existing image and putting some labels on it just to let our users know that we trust this image, that there's nothing else that we need to do with this. We just put some labels to say, we trust this is okay. But again, you can do this from a formula like this. And then in this other example, we use a tool called BC Data, which is for those of us who are of a certain age and we remember doing spreadsheets on terminal. This is a really good tool to do that. So in this case, instead of starting from a simple image and then installing Python, I just used the default supported Alpine Python 3.8 image. So again, you have more than one options. It really depends on the footprint that you want to have and how much granularity you want to have with your containers. And again, you want to see a list of curated examples. Well, we have a lot. Let's see if I can open it. So at PSC, we do maintain a list of about 100. All of these entries that you see on this repository are official Singularity applications that we maintain as Singularity containers at PSC. These are applications that are either installed on BIL or on Bridges too. So we do have different definition files that you can take a look at to have an idea of the different ways you can deploy an application. And in here, you can find applications deployed, like I said, in different Linux flavors, Python, Perl, Rust, you name it. There are many examples that you can find there. And the link is here in slide 57. So again, to recap, LMOD to load software, Slurm to manage the scheduler, Interact for you to do interactive session, and then Singularity allows us to put our applications in containers. Okay, and then we cannot run them locally on, we cannot build them locally on BIL, but we can use the Scilabs remote builder to build them on the web. You can also run them locally. The version for macOS for Singularity is outdated. I would not do it. I would just try to do it on Linux. If you don't have a Linux box, you can run Singularity within Docker in Windows, but that setup, it's a little bit convoluted, but it does work. However, I don't have a Windows machine, so I couldn't provide you a lot of information about that. So let's do something. I have been talking nonstop for 1:30. Why don't we take a 5-minute break? And is that be okay with you, Lydia? Because I have one more topic left.
That sounds great.
Okay, so 5 minutes. We'll see each other in 5 minutes starting now.
That's good.
Okay,
Bye.
bye. I'll be here, so if anyone has questions during our break, just let me know and I'll try to answer them.
So, hello, Ivan. You can hear me?
Yes, I can hear you.
So, just a quick question since you're here. Like, what's the role of Singularity here? I am familiar with Docker, but I wanted to quickly understand what the Singularity is doing.
So
Yeah.
part of the goal of the hackathon is for us to try to create like part of the teams participating in the hackathon is to be able to create containerized versions of their pipelines so that they can become reproducible and widely used. Unfortunately, Docker is not widely supported on most HPC clusters for security reasons. And Singularity is sort of like the default. Singularity and Apptainers are the default technology used for containers in HPC clusters. There was a moment in the past where there was a mismatch between cloud services like Azure or AWS, where it's like, if you're there, you use Docker, and if you're like in HPC world, you use Singularity. But the reality is that a lot of cloud services like AWS do support Singularity at the moment. So slowly we're sort of gearing towards that model instead of using Docker. Docker is still widely used. Don't get me wrong. It's still used a lot. But like if you have access to an HPC machine that is either used by a public university and a nonprofit organization, or like it's a member of Exceed, the probabilities of you having access to Docker on that shared resources is 0 to none. So that's why we discuss alternatives like this.
Thank you.
And the other thing that I would argue is that a lot of people who are pro Docker, they want to maintain or deploy microservices, which is not necessarily the purpose of Singularity in the scope of research, right? Like we just want to, we're just running, we're not trying to run services. We're trying to run applications or very simple software.
And Apptainer, that's just a different name going forward, or? is the-
Yeah, so it originally was Singularity, then Scilabs. I think Scilabs, okay, so let me say this properly. Singularity is the commercial side of Singularity. I don't know how to say this properly. Singularity like diverged into Apptainers and Singularity. Singularity is commercial and Apptainers is going to be open source. But it has gotten confusing because even though they released the alpha version of Apptainers, the binary is still called Singularity because everybody calls it Singularity. So in the next few years, things might change a little bit, but it's going to be the same technology. So maybe next year we'll call it Apptainer, but for now we call it Singularity.
Got it.
So I copied over chat on Zoom another link to a separate document called Intro to CWL Tool. And that is what we're going to be talking about next. Okay, I guess we can start. So we talk about LMOD, Slurm, Interact, and Singularity, and how they all tied up together and using our resources. So the next part I wanted to talk to you about, it's a little bit about the common workflow language and CWL tools, which is the application that works in hand with CWL. So Who has worked with, if you could do a thumbs up, who has used the Galaxy server before? Does anybody know what Galaxy is? Or maybe it's a different scope of applications for people. Nobody, is anybody aware of Galaxy and Galaxy services? Server? No? Okay. So a Galaxy server is a web-based application that can be used to run different kinds of applications that are widely used normally in genomics and proteomics, but it has like a visual interface. So for each of the binaries that you can use on Galaxy, you have a definition, a file that defines not only what your application is about, but you clearly define the inputs and outputs of your application. And the reason you do this is so that you can connect these applications by their inputs and outputs. And then you can sort of create this workflow that is nothing but a connection of applications running next to each other. Most of the time sequentially, not necessarily in parallel. That is sort of like the initial idea. So CWL works works sort of similarly. It says, well, you know, even if you're not a programmer, you should be able to define a list of steps, whether sequential or in parallel, create a sort of pipeline or workflow that if you clearly define your list of inputs, you can clearly also define your list of outputs, so that any person using this sort of description should be able to run your pipeline if they match their inputs or their input files to whatever description you're providing. And if they do that, at the end, they're going to get the output that you define yourself, right? Like if you give it input images and some transformation is happening on those images, and there's a one-to-one mapping, if they give you 10 images and a few parameters, they know that on the other side, they're going to get 10 images as well. So that's sort of like the same idea. I mean, if you think about it, it's also very, very common with some very stable applications that people developed in the past, like Simulink or Stella, that were very common with ODEs in the past, where you had a sort of like what they called it, sort of like a waterfall diagram of inputs and outputs with parameters that you tweak to get different results. So CWL says the same thing. Hey, we can do that, right? Like we can clearly define a list of steps and tell you what tools are running at each time, and then sort of like tell you the inputs and outputs that connects them. And if we do this pretty simply, and then instead of having someone install all these different tools in the workflow, but rather we pull them from the web, right? Like either through Docker Hub or Scilabs. If you're using containers at each of your steps, and these containers are public and people can download it, then maybe your workflow can work out of the box. And that is the basic idea behind CWL. So what we were going to try to do is try to install this is also a guided exercise. We're going to try to install a CWL tool in your user space. So let's try to run these commands on terminal. Okay, so I'm going to go in my case to the desktop. You go wherever you want. I'm going to run interact, and I'm going to get, actually, I'm going to copy that command over here. I'm only getting 2 cores and 16 gigs. That's enough for everyone here. So no one will be. I'm going to run the interact command, and I'm going to wait. It'll take a few seconds. Okay, there we go. So now I'm sitting in node L005. If I run SQ, I see that a lot of you are there with me. You have your own allocation. That's pretty cool. So we're going to be using Anaconda. So that's the first thing that I'm going to do, module load Anaconda 3. So that's absolutely fine. There's no problem. And now I'm going to install the runner. So notice that I'm going to use this pip install user CWL tool. And if I run that second command, it's going to install that application on my user space. And then I'm going to rerun the same command, but I'm going to install Cauce, which is the little dummy tool that I used at the beginning of the presentation. Because we're going to try to create a workflow for a little cow saying hello. And remember, the whole point of Cauce that I used at the beginning for Singularity, which I'm going to use now, is not to introduce you to the science behind it or the possibilities, but sort of to give you a very simple introduction on how to use CWL. Okay, so now it works. If I do Cauce, I don't know, hello, it should print a, there you go. I got my cow saying hello. Okay, so there you go. You can see it in my presentation that it works. So we're going to create a file that I'm going to call Cauce CWL. And that is going to be a YAML file that contains the instructions to run my workflow. Okay, so notice that on slide 62, I have that file, so I'm going to create Cauce CWL. Oh, sorry, BI. Okay. And now let's take a look at this file that I just created. Again, it's a YAML file, so it's kind of like key value pairs. Basically, I'm saying that in this particular workflow that I'm creating, my base call, my base command is Cauce, right? Like that's the name of the binary. And then I'm going to define my inputs. And if you notice the way I run it before, there's only one input argument. And that input argument is that string that I want the little cow to say hello. Okay, so I define a section called inputs, and then I define a single input, which I call message. I tell it what kind of input it is. In this case, it's a string. And it's the first one, is the first position in the list of arguments. This is pretty straightforward. There's one argument, the argument is a string, and that's all I need to run this Cauce application. And the outputs, it doesn't really matter because I'm printing to screen. It's standard output. I could save it to a file, but at this point, I really don't care because it's going to print to screen. So keep that in mind. When you're using CWL to define a workflow, you need to specify the binary or the base command of the tool for your particular step, but you also need to define each of your inputs, including the position relative to the call to the base command, right? So if you were running a tool that has 5 input arguments, then you would have to define where do each one of those go. So any questions so far? No? Okay. Now I'm gonna save it. And now I'm gonna create a file called message.yaml. And remember that my input argument in my CWL file was called message. So just like before, this is a key value pair, and I'm gonna say hello world is my input argument. So now I created 2 files. I created this message.yaml that has the actual message that I want to print. And then I have the cauce.cwl file. Actually, let me, that has my definition of, by the way, I forgot something to tell you on chat. I copied over a PSC GitHub repo that's called Singularity Causae. If you go to that particular repo, all of these files that I'm talking about are there, the CWL and the input messages. So just keep that in mind if you wanna follow me or you wanna see what I'm doing. Okay, again, I need two files. I need my CWL file that defines my workflow, and then I need an input argument file. In this case, I call it message.yaml, right? So if you take a look, here's the message.yaml, and this was the CWL. So how do I run it? Well, I already installed the CWL tool, so I can say CWL tool causae.yaml, and then my message. Let's see if it works. Let's hope it works. There you go. And it did work because I clearly defined a step. My input argument was just a string and there was no output because it's just printed to disk. I could say, hey, save this to a file, and then it would create an output file with all of my outputs. That's absolutely fine. Now keep in mind that now I could take this command that I run and I could build example, or let's just call it causae.sh. Forget that I don't have. And then I can do this, and then I do modulo anaconda. Remember, we use Python, we need to load this. That would load CWL tool. And I just need these two files. So now that I have a causae script, I can do sbatch and submitted to Slurm, and it will run. I'm not gonna wait for it, but it will run. So now you know that if you create you have the binary installed in your workspace or installing in on BIL, then you can simply create a workflow where you're just defining the inputs and outputs and the binary that you're calling. But what happens when that binary is not there? What happens when we cannot install the software on time and you have a deadline? Well, that's when you can deploy your own Docker container. So you can deploy your Singularity containers. So think of this particular example that you'll see on screen. This is a very simple, very straightforward Docker container. Very similar to the Singularity, Docker file, very similar to the Singularity definition file. I am just running the aptitude command that will install causae, and then it tells you that the command is causae. That's very, it's like a 4-liner, okay? So technically speaking, I can build that image and pull it and then push it to the web, to Docker Hub. But like I said before on BIL, we cannot run Docker containers. But what I did is that I pushed mine to the web. So what you could do now is go back to your causae.cwl file, right? And now I can say, you know what, this is so cool, this is so nice, but the causae command is not installed in my system. However, I am aware that Ivan has a Docker container that has the binary that I need. So now I can copy this. Actually, I can copy this and say, you know what? One of the requirements for this particular workflow is that you need to pull that Docker container. And if you do that, then it should, instead of trying to run the local binary, the causae binary, it will try to run a binary that resides in that container. Now, the good news about this is that if you have a workflow, remember the bioformats example where I was running 2 different containers? for my 2 different steps on my single script, you could potentially have a CWL workflow that defines 2 different steps. Each step requires 1 Docker container or a Singularity image. And if those exist in Docker Hub, then the CWL tool will pull them for you. They will run them for you, and they will provide the outputs for you. So your involvement is minimal other than just writing the CWL workflow file. Of course, that assumes 1 or 2 things. Either you're the original developer of the Docker image or the Singularity image, or you trust your collaborator. And that's the main idea of what we're trying to do with this hackathon. Eventually, each team will develop their own containerized application or workflow, and we should be able to build common workflow language workflows, files, that will pull these containers from the cloud, and through a single file, which is this definition that you see on screen, we'll be able to run a complete workflow on a set of images that live on BIL. Okay, now, like I was showing you before, the only difference between this and the previous one is that you're defining the Docker container that you're pulling, someone that you trust, or a container that you know that works, and then you run it locally. However, like I said before, we don't support that on BIL. However, there is something that we do not officially support, and I'm going to show you quickly how to do it, but I cannot guarantee you that it will work, so we can all try together now. You could install uDocker. So uDocker is a tool to run Docker containers, not to build them. So on terminal, type pip install -- user uDocker. And run it. In my case, I already had it installed. So CWL, if you look at slide 68, there is a command at the bottom that uses something called uDocker. If you have that installed, you might be able to run this without converting your Docker image to a Singularity container. But this generally works with well-defined, simple containers. It might not work 100% of the time. So with something as simple as this, it should work. Let's see if it does work. So let's just wait to see if it works, but we're running out of time. Okay, so that's the first thing. In my case, it did work. So uDocker is an alternative to running Docker containers on BIL. Might not work 100% of the time, so test it as you see fit. The alternative is to use Singularity. And to use Singularity, you just need to include the Singularity flag when you're running CWL tool. And if you do that, it will download the Docker container from the web, and then it will convert it to a Singularity container in the same fashion that Singularity does. Now, the only trick about doing this, that it only works if the application within the container is clearly defined, meaning that it has the proper environment variables, and, like it's maybe the binary is present on path. It tends to be a little bit finicky, but if you are creating your own Singularity or Docker files, it's not that difficult to make it work. But just keep in mind, this is how you make it work. Now, like I said, CWLs can be used to create complex workflows for data processing, and then you can pull from Docker registries. Now, just like before in the example with LMOD, what we could use multiple module files, multiple modules in the same script, and with Singularity, where you can have multiple Singularity containers in one script, you can expose as many parameters as you want from your tool, right? So in Cauce, very dumb example, one input argument called message, that's what you print. But in reality, that tool has like 5 or 6 different input parameters that you can tweak to print different things. One example is one called format, right? And then with format, you do not only specify the position, but you can specify the prefix if there is one with your tool and the default value if it exists. So you can choose to expose as many parameters your tool has or have it set some default values so that the user cannot tweak them. That is really up to you. And then if it works, you can get, in this particular case, it printed something different. So you can also choose what parameters to expose, even if your tool is very convoluted, but you're just exposing, just a subset of those for the purposes of this hackathon, then you can limit that through the CWL workflow. And this is a more meaningful example, right? Like Cauce, that Cauce is just very dumb example. The one you can find on slide 75 is the example of bioformats to raw. The only comment that I will make about the workflows is that it's very important for you to clearly define the type of input argument, whether it's a file, a folder, a string, an integer, etc. They need to be very clear so that the workflow knows where to copy them or not. And like I said, this is a more meaningful example where it's saving the standard out to a file. It has the base command. It expects a directory full of images, and then you can specify and expose as many parameters as you want. And that's it. That's basically the plan. The plan is that for you to eventually create a Singularity definition file or a Docker file with your tools or a list of tools, and then sort of wrap them together into a common workflow example so that we can share it with the participants of the hackathon and eventually share it publicly so that people can just download that single CWL YAML file, and that's enough for them to run your pipelines. And I think that's it. I mean, 76 slides is more than enough. Any questions? Well, Lydia, I think I'm done.
Sorry about the background noise. Thank you so much. That was such a great, thorough explanation, and you have lots of things for us to go back and check on things to redo again. And you'll be available to answer questions too throughout the next couple of days.
Yep, no problem.
Yeah. Matt, should we take a little break before the next tutorial? What do you think?
Agreed. Yeah, let's take a 10-minute break.
Okay. And then we'll be back with Jeff and Min to show us how to pipeline a simple registration method.